Hello everybody, welcome back to my YouTube channel. In the last video, we discussed in detail what self-attention is and we covered everything that you need to know about what self-attention is. Everything was explained in a very intuitive manner. If you haven't watched that video, please go and watch that video because positional encoding is related to self-attention. Now let's start this video on positional encoding. So let's just first understand that what is the problem with our self-attention model. If I consider an example, let's say a sentence, cat chased mouse. This is my first sentence, and let me just consider another sentence that says mouse chased cat. Now these are two completely different sentences, right? With completely different meanings. But if I pick cat here and I pick cat from my second sentence, then the embeddings, the contextual embeddings that I will get from my self attention model for this specific word will be exactly the same. The reason self attention model does not capture positions. That is why the words that are occurring in the sentence, our self attention model doesn't care about the order in which these words are occurring. The only thing that it cares about is that if two sentences have exactly same words, then the positional, then this word embeddings, contextual word embeddings of every word will be same, irrespective of the order. But if we look at these two sentences, then it's quite obvious that we must capture the position, right? Because the position in which the words are occurring that determines the meaning of the sentence, isn't it? Because here the cat is acting like a predator. It's chasing the mouse. But if you consider the second sentence, then the mouse is chasing the cat. So the cat is acting like a prey. So that is why, since the meanings are different, their contextual word embeddings should also be different, right? And why our self-attention model fails? Because it does not capture the position or the order in which the words are occurring in a particular sentence. We need to find a way through which we can tell our model that this is the order in which the words are occurring. Now generate contextual embeddings according to that. Now the question is that how we will implement this. A very simple solution can be that, let's say this is our self attention model. Then a very simple way would be then that the word embeddings that we are passing, those are nothing but vectors. For example, let's say this is the vector for my cat. Let's say it contains certain numbers. Okay. The word embeddings that I am passing, at the end, I append one number that represents the position. For example, here in this sentence, the cat is occurring at first position. So for this sentence, the word embedding will be this, and then at the end, we have additional element in the vector 1. Similarly, if I consider the second sentence, then what will be the word embedding? It will be exactly how the upper one is, but at the end, we will have 3 because here the cat is occurring at third position. So one way is that at the end of our word embedding, we pass out the position at which that word is occurring in the sentence. And then the processing happens in our self-attention model, and we get back our contextual embeddings. All good up till here, right? But we have one problem here. And that problem is that these sentences are very small. Consider a very big document that has more than 100 words. The problem with this approach is that this number can go up to any number. It's unbounded. It can be 100, it can be 1000, depending on how many words are there in my sentence, in my paragraph, in my document, right? And because these numbers are unbounded, and we know that in deep learning, the numbers should be normalized, because if numbers are not normalized, then our training will be unstable. So that is why these bigger numbers will cause unstable training. That is why this is not the method that we can use, right? Now you might say that what if we divide this number by the number maximum number we have. For example, let's say if in a particular document we have 1000 words, then instead of giving discrete numbers like 1 2 3 4 up to 10,000, 1000, I'm sorry, what if I use it this way? To I divide every number by the maximum number that I have in the sequence. It will be 3000, and at the end it will be 1, because 1000 divided by 1000 is 1. So by this way, the numbers are now in a particular range, they are not unbounded. So this is a good strategy, right? But no, there is a problem here. Let's say you have two sentences. The first one contains 100 words, the second one contains 1000 words. Now, for first position, what will be our last element of our word embedding vector? That would be 1 upon 100, right? But in this case, it will be 1000. Now, do you see the problem here? For same position, we are now seeing two different numbers. Our model will never be able to find out that what exactly is first position or what exactly is second position, because these numbers are not fixed, which is a big problem, right? So these two methods have failed. Now what we want is, we want something that is bounded, something that is continuous, because we know that discrete numbers are not working for us. Deep learning models like something which is continuous because we have gradients involved, right? So that is why we want something which is continuous. What we want is, we want bounded, continuous thing, right? Now, so what researchers thought, that why not we use trigonometric functions? These are the best way of representing things, right? Because what is happening here, that let's say, let me consider the sine graph. Then what will happen, then this is how my graph will look. Now the values are bounded, the graph is continuous, right? So this is something that we can use. It's the easiest way, right? So that is why researchers thought that why not we use trigonometric function. Now there is one more benefit, and that is very crucial, that I will tell you later, that why specifically trigonometric functions are used. Because there are bounded functions, there are many functions that are bounded and continuous at the same time. Then why specifically are we using trigonometric functions? We will understand this fact by the end of this video. But for now, what we what where we have reached, that the word embedding that we are considering, let's say for cat, we are saying that at the end of it, what we will do, that we will pass sine of the position. So instead of passing 1 directly, now we are passing sine of 1. Now there is a problem here, and that problem is that this graph is periodic. The values repeat themselves, the values repeat after a particular interval. For example, you see that the graph up till here is being repeated again, right? You see the repetition here? You see the repetition here? So if I draw a line here, let's say this line, then for this value, for this value, for this value, for this value, we have the same positions that we will get here. If this is x, this represents your discrete positions, then for this line, all of them will have the same sine value. And if two numbers, let's say at this position, I have certain value, and if at this position I have certain value, then if two different positions represent represent the same number, then that's a problem. Our model will not be able to understand that for this particular value, what is the exact position that we are trying to represent. Is it the first one? Is it the third one? For example, let's say for first and third, we have the same value of sine. Let's just assume that. Then our model will never be able to understand that by this value that we are getting from sine 1 or sine 3, what is this position exactly? Is it first position? Is it third position? We should have unique values, right? So what scientists proposed, that instead of just using sign of position, what if we add another vector here, another element here, append another, concatenate another element here, and that is cos of position. Now the benefit is that now frequency has reduced. Now frequency has reduced. Okay, so this is how the cos graph will look. This is our cos graph. And now the frequency has reduced. So if I draw a line here again, then you see here that the frequency has reduced. Now this line, instead of occurring 4 times, now it is having a similar value at this position, and it is having a similar value at a later stage. Not this frequently. If I just draw this graph more clearly here, then this is your sine graph. Let me pick another color to make the difference clearer. This is our cos graph. Okay. Now, if I draw a line here, let's say this color is not visible. Okay. Let's say this is the line that I am drawing. Okay. This is the line that I have drawn. Now, earlier what was happening, that we were getting same value for this, right? For this, for this, we were getting the same values. But now what is happening, that frequency has reduced, because now you see where is it meeting. For this is the value. Okay, then here we are getting the line, and here we are getting the line. That frequency has reduced. Okay, so that is why now you might argue that this frequency is not that much reduced, right? There is again possibility that they might meet, two different positions might have same sine cos value, or the encoding that we are getting here, that might be still same. Then how do we increase its chances of not meeting with any other value? So the solution is that you add another term. Okay, and you keep decreasing the angle that you're considering here. So since you used here sine of position, here cos of position, now you use sine of position by 2, cos of position by 2. Now the chances of two positions having the same encoding will be very rare if you keep adding this. Okay, if you keep adding this, then the frequency decreases. Now in the self-attention model, how they have in the self-attention model, in the attention is all you need research paper, how they have used these pairs, that they have used an equation y of position 2y equals to sine of position 10,000 2i by d model. This d model is nothing but dimensionality of the embedding. So if your embedding contains 5 elements, then this will be 5. And what is I? I can have values from 1 to d model by 2 minus 1. Same way how we were decreasing the value p by 2, then p by 4, right? Here we are decreasing it this way. Similarly, for 2i plus 1th position, what we will have? We will have cos with the exact same angle. Okay. So this is how it is used in the self-attention model. And the frequency here, where the 2 points meet, it is meeting here, then meeting here, right? I know I haven't drawn this graph properly, but if you will look at these two graphs superimposed on each other, your cos graph and sine graph, I know I haven't drawn it properly. Actually, they should have a common angle um at particular angles only, but I know I haven't drawn this graph properly. So if you just Google the exact graph and superimpose these two graphs together, then you will see that if you consider a single sine graph and you draw a line horizontally to the x-axis, then you will see that the frequency is a frequency of two different x having the same sine x, that is much higher as compared to the graph where you have sine x and cos x, both of those being superimposed, and then you are comparing how much frequently your x values have same sine or cos pairs, right? So that frequency reduces as much as you are introducing the terms, that frequency reduces with the angle. And if you keep adding term, then that further reduces it. Okay. So as many as we have our elements in word embeddings, same way we use positional encoding here. Okay. And what exactly are we doing? Are we appending it this way? We simply add them. We simply add them. And the simple reason is that if we will concatenate them this way, then the dimensionality will increase, the number of parameters will increase, because you know now what happens in self-attention model when this goes inside. If you haven't watched that video, then please go and watch self-attention video and you will understand that why dimensionality will increase, because this is because of the processing that is happening in the self-attention model. So if the dimensionality will be high, then more trainable parameters will be there. So in order to reduce the dimensionality and also incorporating the positional information, we simply add them. We simply add them. We don't concatenate them. We take our word embedding, we take our positional encoding, which is nothing but sine and cos pairs, and every next angle that we are taking, that is half of it. And if we consider attention all you need paper, then it is not exactly half but divided by this term. And we add these two vectors, and then the final embedding that we get, we pass it through our self attention model, and finally what we get is contextual embedding, that is task specific, and that captures the positional information as well, that returns the contextual embeddings based on positional information as well. Now I will tell you that why do we use sine cos pairs alternatively. What is the benefit of using trigonometric function? And the reason is that this is able to capture the relative position. Relative position. Now you will wonder that why are we capturing the relative position? How is it helping us? So see, if I write a sentence here, for example, if I pick the last sentence that we discussed, cat chased mouse, then in this sentence, only capturing the information that cat is at first position, cheese is at second position, mouse is at third position, it's okay, but this is not the right way of capturing information. The better way is that not only you are capturing the absolute information that where that word is lying in the sentence, but you are also capturing the relative position. For example, if I consider mouse, then I must also encode this information that it is coming after chased word, because that is more meaningful for me, right? What is coming before this word, what is coming after this word, that information should also be encoded in our positional encoding, right? So if we consider discrete numbers 1, 2, 3, then the problem here is that we are able to capture the absolute information, but the relative position is not captured here. For that, our model would have to do manual subtraction. But we as humans can see and subtract. But our models that are nothing but deep neural networks, they can't themselves do the subtraction and find out the relative position. That would be an additional overload on them, right? So that is why when we use these trigonometric function, then the difference in position is nothing but the difference in their angles. And this difference in angles can be easily find out by dot product. And this dot product thing they already do in the self-attention model. So once they know that, okay, these two, these two vectors, these two positions, these two positional encodings that we have get, these two have some difference. And since these are sine and cos values, this difference in position, this difference in phase is nothing but the difference in their angles. And this difference in angle can be easily found out by dot product, because this is what we do inside our self-attention model. So indirectly, we also know the relative position of it without doing any manual thing on our end or without adding an additional overload on our model. So this is the benefit. I hope this video on positional encoding was clear and all your doubts were cleared. Still, if you have anything, do let me in the comment section, and please subscribe to my channel because I have been doing a lot of hard work. If you like this video, please give it a thumbs up. Next, we will be covering what batch normalization is and layer normalization is. And once that is done, we will move to transformers, and we will try to cover this deep learning series as soon as possible, because I'm thinking to cover some real world projects as well. So see you in the next video and take care. Thank you.